Hey, grade 10s. So we are now on Unit 7. So like I said, we're near the end of the course now. Unit 7 is pretty short. It's actually just two lessons. Technically, it's four different topics, but we kind of squeeze it into two separate lessons because they're a little bit related to each other. So in today's lesson, we're going to learn about sequences, and there's two types of sequences, arithmetic and geometric sequences. And we're going to talk about what they are and how to distinguish between them. And of course, then we're going to talk about how to describe the sequences algebraically. So what is a sequence? So a sequence is an ordered list of numbers that usually follow a pattern. So there's most of the time there's going to be a pattern that we see here. So for example, 6, 11, 16, and 21. You probably did this even in elementary school. Teacher would give you a list of numbers and you have to try to figure out what's the pattern here. And I think that most of you can see here that we're just adding 5 each time. So that's clearly what the pattern is here. We just add 5 every single time. So that's an example of a sequence. So again, it's a list of numbers that kind of follow a pattern. And you're probably wondering, what does this have to do with functions? So we'll talk a little bit about this. So sequences have a definite end. They can either have a definite end or they can be infinite. So you can have an infinite sequence or you can have a definite sequence, which basically means that it has an actual end. So it stops, and for example, in this case at 21 and it doesn't continue. Or you could have an infinite, which means it goes on forever. Each number in the sequence is called a term. So we have a name for each of them. So each number here is called a term in the sequence. The first term is actually denoted by T1, and the second term is T2, and I think you kind of see the pattern. T3 would represent the third term, and you can pretty much take a guess what T4 is going to mean. T4 would be not your tax returns. I'm not sure if anyone knows about that, but it's going to be your fourth term there. So that is what the T4 and T5 and so on is going to represent. So if we want to know a term in general that we don't like, let's say that there's a specific term that we don't actually know the number for, and we just want to have a general term for it, then we actually call it the nth term. And what the nth term basically means is some term that we are not really sure of, right, at the moment. So this n could represent anything. It could be 5, it could be 10, it could be 100, it could be 1,000. Like, we really don't know what it is, right? It's just some unknown number. And the whole idea in math is we try to find out if there's patterns within a smaller set of numbers, and then we try to see if we can replicate that or we can extend those patterns into a more general understanding of what's happening. And that's really what we're doing here with sequences. We're trying to figure out, once we see the pattern, is there a more general way of expressing the nth term, whichever term you're looking for? So sequences are actually an example of discrete functions because we have a term that is the independent variable, and there is a corresponding value for that term. There's a term value for it. So in this case, our domain basically consists of natural numbers, and that's why it's called a discrete function. Because unlike the other functions we looked at, where the domain was an element of real numbers, in discrete functions, the domain will actually be a set of natural numbers, which means that we only look at the counting numbers, the numbers we count with. So 1, 2, 3, and so on, right? And including 0, by the way. We also include 0, and we'll talk a little bit more about that. And then the range is going to consist of basically the value of the term. So for example, this one right here, this pattern of 5, 8, 11, 13, 14, 17, so on. We can see here that we're just adding 3 each time. But what we do is we specify that the first term is T1, which is 5. The second term, T2, is 8. The third term, T3, is 11. The fourth term is T4 is 14, and so on. And this right here, the numbers at the bottom there, our term numbers, are actually known as our domain. So whatever the term number is, that is our domain, and the range is the term value. Okay, so the range right here is the term value. Again, I'm not really going to ask you this on a quiz or on a test. And again, I think I mentioned this already, that there is no test for Unit 7, just a quiz, and it's only 10 questions. Kid you not, just 10 relatively, I hope, I wouldn't say easy, but relatively okay questions. None of them are, I'm not purposely trying to trick you. Everything on the quiz will be on the lesson, okay? But I'm telling you right now, there's not going to be a question asking you about describing discrete functions. So don't have to worry about the definition, but I think it's more interesting for you to kind of see why it falls under this category of functions, because it kind of seems like a little bit of the odd man out. Unit 7, Unit 8 kind of seem a little bit different than what we've seen before. But I want you to kind of see the connection between what we're doing here and what we've already covered. So the first type of sequence we're going to talk about is an arithmetic sequence. An arithmetic sequence is actually something you're quite familiar with, believe it or not. Is a sequence where you have a common difference between successive terms. So that means that we're increasing or decreasing by the same amount each time, additively, right? So for example, in this sequence, 1, 8, 15, 22, and so on. Sorry, just charging my laptop here. We can see here that we are simply adding 7 each time, right? That's a general pattern that we see here. So this is an example in an arithmetic series because there's a common difference throughout. And we actually answered the first question. What is the common difference? Well, the common difference is definitely 7. How do we use this to help us find the 5th term and the 6th term? And that's what T5 and T6 represent. This represents the 5th term, and this represents the 6th term. And then the last question, just determine a formula for finding the nth term, or T at n. So how do we do that? Well, let's start with the first part. Well, we can see here that the difference between the consecutive terms, such as 1 and 8, 8 and 15, 15 and 22, is 7. So the common difference is definitely 7. I don't think many people can argue that. How do I find the 5th term? Well, it's pretty simple. I know the 4th term. So if I want to figure out what the 5th term is, all I have to do is add 7 one more time, and that gives me 29. And that's T5. And if I want to find the 6th term, I simply add 7 one more time, and I get 36. And that is my 6th term right there. So hopefully that's making sense so far. Pretty simple. I believe you did this in grade 9. So when we first started talking about linear relations, this is actually how we learned about it. And in grade 7 and 8, you probably talked about sequences as well. You probably just didn't have a name for it, but you definitely talked about these patterns. So the last thing is to find the formula for the nth term. This is where it gets a little bit tricky. So you might look at this and think, I have no idea how to start this. There's not really a pattern I follow. But if you go back to grade 9, you remember slope. Hopefully you remember slope. And I know I taught some of you in grade 9. And I'm sure that I said the slope a million times throughout the course. I think I mentioned it to you in grade 9. Basically, slope is the theme of the whole course, right? I want to say like 50% of the course is about slope. So slope basically measures how the rate of change in a relation, right? So how much the y is going up by relative to the x, the change in the x. So notice that the slope in this case, we can think of it, the slope as being 7, because that's how much our y values or our term values are increasing by each time. So we add 7 after the first term that we have there, right? So after the first term, we keep adding 7. So because we're adding 7, but we're adding it after the first term, we actually write it like this. We start by writing 1 because that's our initial amount. This is our initial amount that we start with, kind of like y-intercept. It's similar to y-intercept, not quite. And then the only difference is that before we would write, 7x plus, whatever the y-intercept is. Now we're switching the order. We put the initial amount at the beginning, and I don't want to say initial amount, but I will say the initial term, T1, right? We can see that the first term is T1. And what we're doing is simply adding 7 after the first term. So because we're adding 7 after the first term, we have to really be careful with this. We're not actually multiplying 7 by n. We're multiplying by n minus 1. And again, this should kind of make sense. And I'll kind of erase it so it makes more sense here. If I want to find out what the third term is, let's just do a couple examples here. If I want to find out what the third term is, actually, let's start from the beginning. The second term. I have to add 7, a total of 1 time. To get to the third term, I add 7 a total of 2 times. To get to the fourth term, I add a total of 7 3 times. So we notice that we add the common difference, 7 in this case, n minus 1 times. So it's always 1 less than the term number we're looking for. So if we're looking for the 5th term, you can pretty much follow this pattern. You're going to be adding 7, not 5 times, but you're going to be adding 4 times. And the reason you add it 1 less time than the term value is because, the term number is because we notice that we start adding 7 after the first term. So we don't add, you don't add 7 to get to the first term. You start adding after the first term. So that's because of that. To make up that difference, we multiply by n minus 1. So alternatively, you could look at a different way. If you don't want to think of it as n minus 1, which does kind of confuse people sometimes, you can actually think of it a different way. Instead of us focusing on the t1 or the first term, we can actually go back a step. And we can say, wait a minute, in grade 9, didn't we learn about y-intercept? Well, if you want to use a y-intercept comparison, this is just a different way to do this. You could do that. So I know that t1 is 1, t2 is 8, T3 is 15. T4 is 22. T5 is 29, right? So you could actually go back one step and say, you know what? When we learned in grade 9 about the y-intercept, we need to make sure that x was equal to 0. So we can kind of do the same thing with this too. We can say, why don't we go back to the 0 term? So if we go back one more step and imagine that you're going back to the y-axis, you're trying to figure out what is the original first term, the one that came before the first term that we have there. Well, that would actually be -6. And why is it -6? Again, we actually work backwards. Instead of adding the 7, we subtract the 7. So we realize that we can actually go back one step. And going back one step allows us to see that there's actually a 0 term that is -6. And that 0 term, -6, is going to help us to write the general term. So this is actually very similar to what you did in grade 9. Remember in grade 9, we had an equation for slope, the equation of a line, which was y is equal to mx plus b. Well, the only difference is that instead of y, it's t at n is equal to mx plus b. The slope, again, going back to this, is the common difference. So that should make sense. The slope is the common difference there. And the b, the y-intercept, is simply going to be your t0 term. So it's a term that comes before we start adding the 7s. So another expression that we could have for the general term is 7n minus 6. So if you look at these two, they don't look the same. And the big thing people ask is like, how the heck are they supposed to be the same? Well, I can show you right now. They are exactly identical. So if I take 1 plus 7 times n minus 1, and we expand out the brackets, so we take 7 and we multiply by what's inside the bracket. Again, don't add the 1 and then multiply by n minus 1. Nope, we got to multiply first and then we add the 1. Well, when we do that, we end up getting t at n is equal to 1 plus 7 times n, which is 7n, and 7 times -1, which is -7. And notice what happens here. We have 1 minus 7. What's 1 minus 7? 1 minus 7 is -6. So notice that we get the exact same expression either way. So there's two different ways that we can find the general term. Doesn't really matter which one you prefer. I personally think over time you will start preferring the general term that includes n minus 1. It will actually start making more sense to you. So the general term, how do we find it? Well, we simply first establish what the initial term t1 is. And again, the initial term is not the same as the y-intercept, right? Don't confuse it with that. It's just the initial term, the first term in the sequence, plus n minus 1 times the common difference. And again, the common difference can come at the front here, or it can go right after, because really when you multiply n minus 1 times d, you can switch the order. So I could have put the d in front, but I will just put n minus 1 times d. T at n, of course, represents the general term. The common difference is represented by d, and n simply represents the index of the term. So whatever term you're looking for. So if you're looking for the 5th term, then you're going to be putting t at 5. If you're looking for the 6th term, you're going to be looking for t at 6. And because we learned about functions, you can actually express it differently. You can express it as f at n. That is also acceptable as well. This is a different way that you can express it as a function. So one really interesting thing about this is that this term, like I said, sometimes people prefer to have t naught or t0. We normally call this t naught, but you can call it t0. A lot of people will prefer that way to write the general term, but I want to show you that they're essentially the same, just like we did before. But I'm going to show you in general why they're the same. So again, same idea. If I expand this out, expand the brackets here, d times n is dn, and then d times -1 is -d. Now, one thing we notice here is that we have one term that has a coefficient n, and then the other two terms are actually constants. And again, I think you had a question about this on the culminating task where you had to combine the like terms, and I kind of indicated that you're collecting like terms in terms of x, x squared, and the constants. It's the same idea here. We actually, the main variable we're looking at is n. So we want to put the n's, all the n's together, but in this case, there is no common term. Sorry, there's no like term with n, so we just leave the n on its own. But the two constants can be added together. And so when we do that, we end up getting a minus d. Then we get a minus d plus dn. And notice that a minus d is essentially just the first term, because we already said that a represents the first term, minus the difference. So if you take the first term minus the difference, what are you really getting to? Well, you're really getting to the 0th term. If we just go back one step, so if we're at the first term here, and we go back one step, whatever the common difference is, just like we saw before, we end up at t naught or t0. So notice that this expression right here is exactly the same. So I could actually just say, find the 0th term and then add whatever the difference times the n is, right? So that's a different way of finding the general term. It's really your preference, but I think, like I said, over time, you'll get really used to seeing this expression here. So let's do an example here. So we have 2, 6, 10, 14, and so on. So first thing, what is the common? Find the next three numbers, find the 10th term, and then finally write an expression for the nth term. So let's start with the first part. The next three numbers, obviously, we're just going to keep adding whatever the common difference is, which is 4. Pretty simple so far. So if I want to find the next three term numbers, I simply add 4 each time, and that gives me 18, 22, 26. Easy. The 10th term. So to find the 10th term, I know that I need to find the general, I could find the general expression, or I could just keep going with this, especially because I'm quite close to it. I could look at the general term, but because I'm quite close, I can just keep going. So again, this is T5, T6, T7. So I'm just going to keep going. I'm going to keep adding 4 each time. That gives you 30. And then I add 4 again. I end up getting 34. And T10 is 38. Oops, sorry, adding 4. So that means that my 10th term is 38. For the last part, to find the nth term, I need to know the common difference, which is 4. So d is equal to 4. My t1, or my a value, is the same thing, is equal to 2. So what I'm going to do is I'm going to sub this into my general expression. I take 2 plus 4 times n minus 1. Again, this is simply the a plus the difference times n minus 1. And when I do that, I could expand out the brackets. And when I expand out the brackets and add the like terms, I end up getting, and I'll show you here, 2 plus 4n minus 4. And of course, we know that 2 minus 4 is negative 2. And then we add the 4n, and then we're done. So we end up getting negative 2 plus 4n. Now, a different way to do this is to actually look for the 0th term. So I already mentioned that. You could actually do this separately. You could start with the first term here, and then you could work your way backwards to figure out what the 0th term is. So to find the 0th term, you're just going back. Instead of adding 4 each time, you're actually subtracting 4 to go backwards here. And that means that the 0th term would actually be negative 2. So you simply subtract the 4 from the first term, and then you end up with negative 2 there. So that is what our 0th term is. So because of that, we can actually rewrite this. We can rewrite the general term as, of course, we write t at n is equal to negative 2 plus 4n. So notice that you actually get the exact same answer as we have here. It's not different at all. You can also substitute 10 into n, and then just check that the general term actually works. So that's a good way to verify if the answer is correct. And not just for T10, you could do this for, the 3rd term. So if you have your general term and you're like, I wonder if this works, well, sub it in, right? Try it with a couple of values. So the 3rd term should be 10. We know that because we are told the 3rd term is 10. So if I sub it into this equation, let's see if I get the same answer. So I'm going to take negative 2 plus 4 times 3. And I know that negative 2 plus 4 times 3 is 12. And then I get T3 is 10, which is definitely correct. So I'm on the right track here. I know that this 3rd term is 10, and so it actually is correct. And then, of course, to find out if it works for the 10th term, you can definitely do that, sub it into your equation, and just check the 10th term is 38. So this is correct. Let's do a couple more examples. So the next one, we have 7, 11, 15, 19, and so on. And then we have 24, 21, 15, 18, 15, and so on. So the first one here, we notice that it is a sequence where we're adding 4 each time. So because we're adding 4 each time, that means that the difference is 4, and our initial value, a or t1, I'm going to stop writing that as much, t1 is 7. So that means that our general term is going to be 7 plus 4 times n minus 1. Again, we can expand out to 4. And if we expand this out, we end up getting 7 plus 4n minus 4. And then we know that 7 minus 4 is 3. So we end up with 3 plus 4n. So both answers are acceptable. Just, you could either write this or you could write this. Both of them are totally acceptable. That's fine. For the next part, we're given that the initial number is 24. The d value is -3. So how could I find the sum here? Well, again, why is it -3? I want to make sure we understand that. It's going to be -3 in this case because we know that we're going to be decreasing. We're subtracting 3 each time. So because the d value is decreasing, then we just make sure that d is equal to, because the values are decreasing, to make sure that the common difference is negative. So when we do this, we end up writing 24 minus 3 times n minus 1. And again, we expand this out. -3 times n is -3n, and then -3 times +1. -3 times -1 is +3, and of course, 24 plus 3 is 27. So we end up at 27 minus 3n. And of course, the different way you could do this, you could go back to the 0th term, which we already discussed, and figure out what term comes before you start subtracting a 3 each time. That means that this the 0th term would technically be 21. Oops, not 21, sorry, 27. Sorry, I was going the other way around. So again, instead of subtracting the 3, we actually notice that we'll do the opposite. If we go in the opposite direction, we add 3. So that is technically the 0th term. We could use that to find the general term. So let's look at an example where we have to determine the number of terms given to us. And then we're going to use this to find the general term. So determine the number of terms in the arithmetic sequence. So we are given the numbers -3, 1, 5, 9, ... 117. So first thing with this question is you have to figure out what the number of terms are, which is basically n. So that's what you're really looking for. I forgot to mention that there, what we're literally looking for is n. That's our goal here. So we want to figure out what n is. We can find the first difference, I hope. And to find the first difference, you can actually just look at the first couple values. So I can see here that I'm simply adding 4 each time to the sequence. So that means that the common difference is 4. So we can start with that part there. We know that the common difference will definitely be 4. We're still not done with this yet though, right? The problem here is that we don't know the n value. So what do we know so far? Well, I know that my first term, t1, is -3, and I know that my last term, whichever term it might be, I have no idea how many terms there are, it's going to be 117. So if we find the difference between the first and the last, that will help us because that will tell us the total difference between the first and the last one there. So what we're going to do is subtract 117. We're going to take 117 minus -3, which means that we end up with a difference of 120. So because the first difference, or the difference between the term values, is 4 each time, we're adding 4 every single time, then we can take the total difference there and simply divide by the common difference. And now to find the number of terms, all we have to do is add the 1. I'll explain why we add the 1. This is the part that throws people off. And I hope logically this makes sense so far. What we're essentially saying, and I'll erase this so it makes sense again. What we're essentially saying is that there is a difference of 120 between the first and the last. And we know that each time we move from one term to another, we add 4. So if we want to figure out how many term values, how many term numbers are in between them, or how many numbers are in between them altogether, or just in total, how many are there? We know that it's going to be a total of, and well, in this case, how many numbers are in between them? You want to think of it that way. How many numbers are in between them? Well, we know it's going to be a total of 120 divided by 4. So we take the total difference between them and we simply divide by 4 because there's 4 numbers in between each of those consecutive terms, right? So it makes sense that we would take the total difference and divide by the common difference, and that will tell us how many terms are between. So that's the terms between T1 and Tn. So we're not done yet. That tells us how many terms are in between them. So why did I have to add the 1 there to find the total number of terms? Well, the reason I add the 1, again, same idea as before. We actually have one more term than just the number of terms between them. So I'll give you an easier example. Let's say that the sequence was something really simple. It was 1, 5, 1, 5, 9, 3, 1, 5, -3, 1, 5, 9. If that was the case, we could clearly see here that the difference between -3 and 9 is 12. Then we take 12 and divide by 4. And that means that there would be 3 terms between them. So I feel like it's helpful sometimes to look at easier examples or smaller examples. We can see that there's 3 terms between them, between T1 and T4. Now, why is there only 3 terms between them when there's actually a total of 4 numbers? And this is what throws people off. Because you look at that and you're like, well, there's definitely 3 terms between them, 1, 2, and 3. but there are a total of 4 terms. So the reason we have to add the 1 there is because we don't actually start adding, we don't start adding the reason, we don't start adding the common difference of 4 until after the first term. So because of that, we need to consider the fact that we didn't add the common difference of 4 to get to the first term, but it still is in the list. So because of that, because we started adding the common difference of 4, just like with the same rationale as before, we have to add the 1 because we kind of miscounted, right? Think of it that way. We undercounted. It's almost like we completely forget about the first term. We're like, oh yeah, right, there is a first term. But the reason we didn't have to consider it in this calculation is because we didn't have to add anything to get to we didn't have to add a common difference to get to the -3, unless you go back to the 0th term. But again, I try not to confuse you as much now. I'm just kind of focused on looking at T1 and so all the way up to Tn, right? You could look at the 0th term, but I'm going to try to avoid that as much as I can now. So for that rationale, because we had to account for that extra term, we need to make sure that we actually add a 1 to the quotient, the total difference between the total difference divided by the common difference. So when we do this, again, I'm hoping that this is kind of starting to make sense now. When we do this, this is going to give us a total number of terms that are there. And again, if you want a more clear example, think about a small easy example. You can see here that there are a total 4 numbers, but the numbers between them, the number of values between them is actually only 3. And again, it's 3 instead of being 4 because the -3, we start adding the 4 after the first term. So we had to account for it by adding a 1 at the end. So we added 1 to the quotient there. So we end up with this expression here. Now, this is a more general way to find the nth term. So I want to show you how I actually got this. Well, this actually comes from this formula right here, which we already have. We know that t at n is a plus n minus 1 times d. So if I wanted to find out the n values, it would just be a matter of rearranging this formula. And again, rearranging means just isolating for a different value. So in our case, we want to actually isolate for n, because n is what we would be interested in. We want to know how many, our goal here is to figure out how many terms, how many terms you have in the sequence, right? Number of terms. That's really what we're interested in. So if we want to figure that out, it's just a matter of rearranging this expression. So what I want to do first is I want to actually take away a from both sides. So I take away a from both sides so I can get n minus 1 times d on its own. And again, the whole idea is to try to isolate for n on its own. So we end up getting t at n minus a is equal to n minus 1 times d. What's our next step here? So our next step is to divide both sides by d. And again, the reason we're dividing by d is so I can get the n minus 1 on its own. That's always my ultimate goal, to get the n minus 1 on its own. So you divide by d, and then you end up with t at n minus a over d is equal to n minus 1. Now we're almost done. Notice that we ended up with n minus 1 on its own, but we actually just want to know what n is. So luckily, the last thing is actually quite easy. You see that -1 right there. So n minus 1, do the opposite of subtracting 1, you add 1. So that means we end up with t at n minus a divided by d plus 1 is equal to n. And this is gonna be the expression that will tell me how many terms I have in a sequence. So if I have a sequence, I can easily figure out how many terms I have by using this formula there. So I hope that kind of makes sense. And that kind of helps clarify how we can find the number of terms. Again, that's a formula. I wouldn't necessarily suggest memorizing it, but I hope you understand how we derive it. So the next part of the lesson is geometric sequences. So geometric sequences have a common ratio between the successive terms. So it's not a common difference, they have a common ratio. And actually, nice little tie in with what we just did in the last culminating task. So I actually asked you to find the common ratio. The common ratio is basically when you divide the consecutive y values. So a common ratio means that we are increasing or decreasing multiplicatively by the same amount. So the terms in this sequence is basically found by multiplying the previous terms by the same amount, the same common ratio each time. So if I want to find the general term for a geometric sequence, we can actually kind of follow the same. We can start by following the same logic as before. So if I give you something like 2, 6, 18, 54, ... and I ask you to find a general term for this. Well, the first thing you realize, hopefully everyone sees this, that you're actually multiplying by 3 each time, right? We're multiplying by 3 every single time. So this is definitely, oops, and I'm supposed to be a multiplication sign. I'm getting a little lazy here. Sorry, let me just fix that. So I'm multiplying by 3 each time. So when I multiply by 3 each time, I can clearly see here that I'm finding all the I'm basically multiplying by 3 to get to every successive term that I have there. You could also figure out what the common ratio is by simply kind of doing the opposite. So it's kind of like if you think about first differences, similar idea, right? I give you a table of values for X and Y, and you want to find the first difference, which is the difference between the Y's, to figure out what the slope is. Well, it's the same idea here. What you're going to do to find out what the common ratio is, you simply take two consecutive points, one after another. So you take the term value that you have now, and you divide it by the term value right before it. And this is going to give you the common ratio. Now, if this actually is the common ratio throughout the whole sequence, we should have the same answer for every pair of consecutive terms that we have. Consecutive meaning back to back, right? That's what consecutive means. So if I take 2 and 6, and I take 6 divided by 2, and then 18 divided by 6, 54 divided by 18, I should get the same answer each time. And I can verify T2 divided by T1. So second term divided by the first term is 3, and the fourth term divided by the third term is also 3. So the common ratio is definitely 3. And we start adding, and because we start multiplying by the common ratio 3 after the first term, 2, and again, similar idea to before, because of that, we have to take that into account by simply raising the 3 to the power of n minus 1. So we're essentially multiplying by 3 each time, but we don't start multiplying by 3 until after the first term. So because of that, the number of times that we multiply 3 by itself is going to be n minus 1. So again, this is just very similar to before, how we said we have to take into account that we don't actually start multiplying by the common ratio, or we don't start for arithmetic sequences, we don't start adding the common difference until after the first term. So because of that, we have to, so in general, here's the general term. So we have t at n is the general term. A is the first term, T1, same idea as before. Common ratios are, and the index of the term is n. So it's going to be the T1 is the first term. I think you understand this idea. T2 is the second term. Oops. T2 is the second term there, and so on and so forth. I think you kind of see the pattern there. So very similar to what we saw before. Again, to find the common ratio, this is in general. And again, this is more of an algebraic expression, which sometimes can be a little bit tricky, but I do want you to start getting more comfortable with understanding algebraic expressions, because you're going to be seeing this a lot more. You're going to start seeing more general terms, and you need to be more familiar with this. You're not always going to see more concrete numbers. So what we see here is that if I want to figure out what the common ratio is, I'm basically saying I can take any term t at n, and again, t at n represents any term, okay? So any term. So as an example, it could be T6, T10, T20, it doesn't really matter, any term, you name it, right? And what we're saying is we're going to divide that any term that we have there by the term before it, So the term that came right before it, right? And that's essentially what we're saying. We're taking that term value that we have, any term value we have, and dividing by the term value that came before it. So again, t n minus 1 is simply the term before the term that we're looking at the moment. So if we have, as an example, t 100, then that means to find the common ratio, I need to divide t 100 by t 99, right? The 99th term. That kind of makes sense. Just basically like what we did in the last example. So let's look at an example here. We want to find the geometric sequence. So we have the geometric sequence below. We want to determine t at n, and then we want to determine what t7 is. Okay, well, you might be already be able to find it, but if it's not that clear, I recommend actually taking t2 and dividing by t1, taking t3 dividing by t2, and even just do it a couple of times, and you'll start to see a pattern. So if we take -3 and I divide by 6, that gives me -1/2. So negative divided by positive is a negative. We do the same thing with the next group. So I take 3/2 and I divide it by 3. When I do that, remember, I multiply by the reciprocal, and this is a 1 there. So it becomes 3/2 times 1/3. And of course, the 3 cancels out, and then we end up with +1/2. -1/2, because it's a negative. I forgot the negative sign there. So we end up with -1/2, and then we can continue this on. So I can clearly see here that the R value is -1/2. Again, if the R value isn't that clear, I definitely recommend that you actually go through the work of finding the common ratio. And again, you do that by taking successive terms in your geometric sequences and dividing them. Okay, so taking the one you have now, dividing by the one that is previous to it. Okay, so it's just like first difference. It's T2, and that one you take y2 minus y1. You take the term value you have now divided by the term value right before it. So I can see here that R is -1/2, not +1/2, and definitely don't confuse it with 2, because sometimes people kind of do the opposite, and then they actually think that it might be multiplied by 2. It's actually multiplied by 1/2. Again, we don't technically talk about when I think I mentioned this already. we're talking in geometric sequences, we notice that there's a constant multiplicative change. We don't normally tend to think of it really just multiplying by a reciprocal, right? So we actually think of it as multiplied by -1/2. You could think of it as dividing by -2, but we don't think of it that way. We just think of it as multiplied by -1/2. So you write 6 times -1/2 to the power of n minus 1. And again, the n minus 1 is coming from the formula, right? We always, remember, we start multiplying by -1/2 after the first term. So we have to account for that. So we could express this as a geometric sequence if we wanted to. We could write f at n is equal to 6 times -1/2 to the power of n minus 1. So to find out what T7 is, we simply take our general term here and we replace n with 7. So when we do this, we get -1/2 to the power of 7 minus 1. Again, always do exponents first. So you got to figure out what's in the exponent. So 7 minus 1 is 6. And then we end up getting -1/2 to the power of 6. -1/2 to the power of 6. Again, this is using your power rules. We know that this really just becomes -1 to the power 6. You can think of it this way: -1 to the power 6, -2 to the power 6. But of course, because it's a negative base and an even exponent, you know it's going to be positive. 1 to the power 6 is just 1. 2 to the power 6, you can do the math there, is 64. So we end up with positive 1 over 64. And of course, when we multiply by 6, we end up with 3 over 32. And then that is the reduced answer there. So I hope that kind of makes sense so far. That's essentially how we figure out the 7th term there. Let's look at another example. So find the general term for the following sequence. So first thing, you want to figure out what the common ratio is. Again, this one's not as obvious because the numbers are quite a bit bigger, but use the same idea as before. So simply take the y value you have now divided by the one before it. So 6,750, you're going to divide that by 10,100. Another two pairs, I could do 4,500 divided by 6,750, and you would still end up getting 2/3. So you can try it out yourself. If I take 4,500 and I divide by 6,750, so I noticed that I can divide each of these by 50, divided each of these by 50. So when I do that, I end up getting, and again, you can definitely use a calculator if you want, just to verify that you are correct on this. So if I divide this by 50, I end up getting 90 here. And then of course, for 6,750 divided by 50, that ends up giving me 135. This actually might remind you of angles. Remember when we talked about quadrants? So 90 degrees, 135 degrees, I can divide both of them by 45 degrees. Maybe you remember that, maybe don't, maybe not, that's fine. You divide them both by 45 again, so you can reduce it, divide them both by 45, and you end up with 2/3. So it is definitely the same common ratio, right? So in our case, the R value is 2/3, and then the A is the first term is 10,125. So our general term is just going to be 10,125 times 2 over 3 to the power of n minus 1. Again, we always include the n minus 1 because we account for the fact that we don't start multiplying by the common ratio right away. It increases exponentially each hour. So by the same common ratio, in 3 hours, there are 135 B's. In 5 hours, there are 1,215 B's. So use this information to figure out how many B's will be there after 8 hours. So what I want to do first is, obviously this question is a little bit different. I don't exactly know what the common ratio is. It's not that clear because I wasn't actually given a sequence. And we also don't know what the initial population is as well, or the initial term, T1. So because of that, we have to kind of tackle this a different way. Let's just write down what we know. Well, I know for a fact, and again, I don't know the formula, but I know that the formula is set up the same way. It's A times R to the power of n minus 1. So in our case, for T3, I simply let the n equal 3. And when I do that, I end up getting A times R to the power of 2. And so then I end up with A times R to the power 2, which is equal to the T3 term, so the third term, which is 135. So that means that AR squared, and again, it's AR squared because 3 minus 1 is 2. So that means that AR squared is equal to 135. Can we do this for the fifth term? Absolutely. We're going to follow the exact same step. For the fifth term, we would take A times R to the power of 5 minus 1. Again, we don't know what A or R is, but I can at least sub it into the formula that we have so far. And 5 minus 1 gives me 4, and then I end up with AR to the power 4. A times R to the power 4 is equal to 1,215. So now that I have these two pieces of information, how can I solve for A and for R? Well, this is kind of similar to what you did. Similar, not the same. It's not the same concept. but it's similar to what you did in grade 10 when you were solving for two equations, two unknowns. If I have through, and I could do this in a couple of ways to figure out what one of the values is. And again, once you know what one of the values is, you can easily find the second one. It's not too difficult. Let's start with the easy part. So what I would do next is I would say, well, I know my common ratio. So let's go back to what I know. I know that the common ratio is found by comparing the consecutive terms. Now, in this case, they're not consecutive terms exactly, but they are near each other. So I can take t to the power 5 and that can divide by t to the power 3. And when I do that, let's do the math here. I end up with ar to the power 4 divided by ar to the power 2. What ends up power 4 divided by r to the power 2? That gives me r squared. And notice what happens with the actual values themselves. The actual term values themselves, we get 1,215 divided by 135, and that's equal to 9. So this is when you have to use a little bit of logic. Use your logic skills now. If I know that r squared is equal to 9, what does that mean about the r value? Well, that means the r value has to be 3. Now, keep in mind, a good question would be, could it technically be -3? So technically, in this question, because we are actually because we're looking at, the third, all we're given is the third term and the fifth term, there is actually a possibility that it actually could be -3, right? But just for simplicity's sake, we are going to just assume that it's going to be the positive case. On the test, I won't give you something ambiguous like that. I'll make sure it's a bit more clear. So in our case, we assume that the r value is 3. So we have the r value, which is 3. So I can now take that r value and I can sub it into my I can sub it into my original equation, either T3 or T5, to figure out what first equation, because it's probably a little easier. So I know that AR squared, right? We were told that AR squared is equal to 135. So I take my A value, which I don't know, that's okay, but I know my R value now. So I take A times 3 squared is equal to 135. Again, figure out what R squared is, that's 9. So now I have A times 9 is equal to 135. Now divide by 9 on both sides, and then I end up with 15. So that means my initial value is 15. So now that you know your initial value and your R value, you can simply sub that into your general expression. So we have the general expression where A is 15, R is 3, and we have to the power of n minus 1. So a different way you could do this, so I just want to show you a different way. And people always will point this out, like this seems complicated, right? Is there an easier way to tackle this? So because the actual terms that are given to you are not that far away from T1, because really your goal was to figure out what A was, right? A and then R. But again, if you're able to figure out what A is, you can definitely figure out what R is. What you could do is you could say, well, you know what? I know that between, if I have, again, this is a different way to reason this. I know T3 and T5 are right here, and I know that this is 135. This is just a different way you could reason this problem. This is 1,250. So you could think to yourself, there are two spots between, they are two terms away from each other. So that means that whatever the common ratio is, I have to multiply by the common ratio twice. So you can kind of reason this out this way. You can say, I'm going to have to multiply by the common ratio not once, but twice, because I have to go to the fourth term and then to the fifth term. So that means that whatever the common ratio is, I'm going to take, I'm going to have to multiply 135 by the common ratio twice, to get to 1,215. So you could reason this and say, R times R. Was there an easier way of writing that? Absolutely. I can write that as R squared. So I have 1,215 is equal to 135 R squared. I can divide by 135, divide by 135, and I end up getting R squared is equal to 9, and then I get the R is 9. That's R is equal to 3, just by the same logic. Another way that people do this is they say, you know what? And again, everyone's different with this, but I find some people are just better at kind of seeing these patterns. So you look at this and say, how much is this increasing by multiplicatively? So if you want to figure that out, you could simply take 1,215 and you divide by 135. And then you end up getting 9. You might realize, it's increasing by 9. But remember, the 9 that I'm increasing by, the total of 9 that I'm increasing by, so this is how much I'm multiplying by to go to 135, from 135 to 1,209. You can actually see this and say, actually, 9 is actually made up of R times R, some number multiplied by itself. So you might be able to reason through this and say, hey, some number multiplied by itself gives you 9. What number does it have to be? That means that the R value must be 3. So you could also reason it through it as well. And then, of course, once you know what the R value is, once you know that R is equal to 3, you could definitely reason this out a little bit easier. You can tell yourself, well, if I want to figure out what T1 is, I can actually work backwards because I'm actually quite close to the first value. So if I know that the third term is 135 and I know the common ratio is 3, I simply divide by 3 to work backwards to get to the first term. So if I divide by 3 each time, I'm going to get back twice, I get back to the first term. So I divide by 3, I end up with 135 divided by 3, that gives me 45. And then 45 divided by 3 gives me 15. And then this would be the first term that you have there. So I feel like that is actually an easier way to kind of reason through this. And I would definitely suggest it made sense. I know that there was a lot of little missing parts to it, but hopefully that's one of the solutions that I kind of showed you makes logical sense to you. Recursive formula. So I'm going to go over this really briefly. I'm not going to spend too much time on this. Basically, there is a different way that we can express a general term. So we can express it in terms of the previous terms. So when we have an arithmetic sequence, we can actually rewrite it a little bit differently. We simply state that the first term, T1, is A, and then we simply say that whatever the general term is, we simply add the common difference to the previous term. So again, Tn minus 1 just refers to the previous term. So if I were to, this is more kind of I always like to be honest with you, I'm not a big fan of the recursive formula. It's not going to be something on your test. And the reason for this is because I don't find it as useful when you're actually, this reminds me more of the elementary way of doing this, right? Which is essentially to kind of describe the pattern, right? So in elementary school, you might have something like this, like 4, 9, 14, 19, and your teacher might have said, okay, what's the pattern? Well, you add 5 each time. So essentially that's what you're saying here. You say, you take the previous value, Tn minus 1, and you add 5 each time, which is the common difference in this case. So for the geometric sequence, it's the same idea. We say that T1 is A, and then we simply state that the next term that you're looking for, the general term you're looking for, you simply take the previous term. Again, this represents a previous term, and we are multiplying it by the R value, whatever the common ratio is. So note that this is just a different way to express sequences. It's not as commonly used, and I'll be honest, it is not going to be in your test. So I would not even bother with these questions, quite honestly. I don't think it's that important, if I'm being quite honest. So I wouldn't bother with these questions, but I just want you to be aware that if the textbook brings up the recursive formula, that's what they're talking about. And basically, a rule of thumb, you can ignore those questions. You have all authority to do that. So here's an example. I'm going to show you how to do this. Again, not testing you on this, but I just figured you should be at least aware of it so that you can at least say, okay, I recognize that form. I at least know what it's referring to. So in this one, we're asking to find the general term, and then we'll do it in 2 different ways. So first thing I notice is that it's decreasing by 11. And the next one, I notice that this is actually going to be geometric. I'm multiplying by 2 each time. Notice that I'm not multiplying by -2. I'm multiplying by +2 because the sign doesn't change. So in the first one, we have an A value of 31 and a common difference of -11. So because, and again, it's common difference of -11 because we're subtracting by 11 each time to get to the previous value. So I write that out as 31 minus 11 times n minus 1, or if I expand out the brackets, I get 11 times n, and sorry, -11 times n, and -11 times -1. And this ends up giving me 31 minus 11n plus 11. And of course, 31 plus 11 is 42. So the recursive formula, how could I do this? Well, with the recursive formula, I basically state what the first term is. I have to state what I'm starting with first. And then what I say for the recursive formula is I say, take the previous term, right? So this is the previous term. And this is like a general rule that we're going to do. So we take the previous term, and then we subtract 11 each time. So if I want to find the next term, I'm basically saying step by step what we're doing. Take the previous term and subtract 11. Take this previous term and subtract 11. Take the previous term and subtract 11. That's essentially what we're saying with the recursive formula. We're kind of saying it more explicitly there. So that's essentially the rule there. For the next one, we notice that the A value is -11 because that's my starting point. I already mentioned this. The R is 2 because we're multiplying by +2 each time, not -2. Just be careful with that. So then we end up with T at n is equal to -11 times n minus times 2 to the power of n minus 1. And of course, I noticed that recursively, how I could write this is I still state my first term, -11. And then I simply state that my general term, T at n, is going to be 2 times the previous term. Whatever previous term I had, I'm going to multiply it by 2 to get to the one that I have now, to the current term. So I'm just kind of saying it a little bit more explicitly as to what the geometric sequence is doing. So the last little thing I want to talk about is good. Hopefully it's a helpful visual here. Arithmetic sequences and geometric sequences, sometimes people do tend to get them confused. And again, On your quiz, I will be honest, I'm not always going to specify whether it's geometric or arithmetic. And that's going to be the tricky part sometimes, is that if you're kind of doing this in a rush, people tend to get this wrong. So a good way to remember this, arithmetic sequences are very similar to linear functions. So you almost want to think of them, they're not quite the same, but they're very similar to linear functions, that there's a constant difference that we're increasing by or decreasing by each time. Whereas geometric sequences are similar to exponential functions. So whenever we talk about exponential functions, well, in exponential functions, we increase multiplicatively, right? So we're either increasing or decreasing multiplicatively by a common ratio. So if you kind of remember that arithmetic sequences are similar, not quite the same, but are similar to linear relations. And if you remember that geometric sequences are somewhat similar to exponential relations, not the same, but somewhat similar, then it kind of helps you to define the relationship between them, right? And if you remember all those key things about exponential functions and linear functions, I think it's worth it, because then you don't have to worry so much about memorizing all the formulas. You actually realize that there's a lot of overlap with what you've already seen. So there are the questions, guys. So again, it's a lot of homework, but to be quite honest with you, you do not have to do all of it. A lot of the questions are a little bit repetitive, but I definitely suggest that you do some of the harder ones. Don't skip if you're going to skip anything, skip some of the easier ones. Don't skip the harder ones. Make sure you practice with them. And again, they may not all be on the test. I'll be on it, sorry, on your quiz. The quiz is going to be relatively easy, but it's good for you to know how to do this, because you will definitely need to know about sequences and series for your IB exam. So make sure you practice with this. All right, guys, best of luck with the questions, and see you soon.